We will now cover the second part of complexity analysis. At the end of part 1 of the lecture, we use algorithm from the GCD problem solving as an example to demonstrate how we can begin to look at the way where we can measure the performance of algorithms. And one of the idea that was utilized at that time is that we simply just count numbers of operations. But we are not just interested in the small examples. We are particularly interested in how different algorithms will perform when we increase the input size. So the formal definition that we will be focusing on for the whole class is when we say a particular algorithm is efficient, it basically means that when you increase the input size, the numbers of operations, or like more realistically, the running time should be demonstrating a slower growth rate. So this is one example. This is the reason why we will focus on the growth rate instead of just looking at the numbers of operation. And here you can see that we actually have two different type of algorithm. The first one, the increase, the growth rate of the operation is 3 times n represent the input size. For the second line over here in red is actually n squared divided by 3. So you can see that although initially it seems to be the case that the blue line is actually above the red line. But because n squared is growing much faster than n, so eventually at the point of input size 9, the red line will greatly outpace the blue line. And after that, there's no turning back. The differences between two lines is growing larger and larger. So I think this is the reason why we do not focus on the numbers of operation at a particular size only. We will just keep imagining what if the algorithms is being used on inputs that's growing in size. So when should we stop? I think this is a natural question to ask if we want to just keep increasing the input size. So in our analysis, we focus on what we call the asymptotic analysis. It basically means that we want to find out the behavior of the algorithm when we are in the limit. It basically means that we want the input size to grow larger and larger and larger. So again, preferably it will be towards infinity, but in reality, you cannot really reach infinity. So in your mind, just imagine that we are looking at the cases where the size really grow very, very large. You can imagine it can be millions, it can be billions even. So why do we look at the case as in the limit? I think simple reason is that when the size is really small, it runs very fast anyway, regardless of your complexity. So what demonstrates the superiority of certain algorithm is really when the size grow to be very large. That's why usually we'll focus on the case where that's really in the limit. And also, I mean, one principle that's deriving out of this is that because we are interested in the limit performance, so it also means that when we look at the performance of the algorithm, we'll be focusing on the worst case scenario. So why do we look at the worst case and not, for example, the best case scenario or the average case scenario? It's not because we are pessimistic. It's simply because best case usually very rare. It's a special case. It doesn't really apply to most of the inputs. So best case is not representative. But how about average case? It's appealing if we are able to do it easily, but in practice it's not easy, and a lot of times it depends on the kind of data that we actually have on hand, right? Because average really depends on what kind of data, what kind of instances you are solving. If you do not have a good understanding of that, there'll be no way you can quantify the average complexity. So that's why usually we will look at the worst case scenario that will tell you really how difficult the problem is in the most like pessimistic way of evaluation. So this is where we'll introduce the big O notation. Big O notation allow us to capture the worst case scenario. So big O is basically uh, representing a very large class, right? So for example, n squared over here, if you enclose that with big O, it represents actually many different ways where the algorithm can demonstrate certain behavior. But like in most cases, the growth rate will be according to n squared, right? So this big O n squared means that the algorithm's order of growth rate will be n squared. If you have a n cube, then basically means that the growth rate will be in n cube. So the benefit of using this big O notation instead of using the exact count is that you can have multiple algorithms. The exact count might be different from algorithm to algorithm, but if their growth rate are all very similar, that follows, for example, n squared, well, we can actually categorize them within the same class. We say that they are asymptotically equal in terms of their performance. And this is one example. This is what we mean by categorizing multiple algorithms that belong to the same class. This O1 basically means that you can see that all the lines are flat in response to the input size. It means that no matter how you increase the input size, the growth rate will stay, will not really grow, right? It means that it stay flat. So you can have a flat line at 1, flat line at 5, flat line at 10. Uh, all of them actually demonstrate the same growth behavior. So although their height are not exactly the same, this execution time may be 1, this is maybe 5, this may be 10, but we call them in the same category, right? So this is the constant time category. The second example, this is linear time, right? So you can see that we can have n, we can have a 2n minus 1, 3n plus 8, so on and so forth. You can have your different slope, you can have your different constant term. So the shape of the line are not exactly the same, but if you look at the response of the three different lines in the input size, the response are all linear. Like with the increase of the n value by 1, you know that the increase in the numbers of operation will be constant. That will be represented by the coefficient over here, right? So behavior, the growth behaviors are exactly the same, although the exact count are different. So because of that, we consider them as belonging to the same category. So you can actually generalize that. You say that, okay, not just O1 or ON, even for a more complicated function, you can still have very similar ways of treating them. Right? This is one example where you have different n square function, and then you have different n cube function, right? So they all the lines over here are looking differently, but they all fall into the same category because their response to the input size are exactly qubit. So this particular table over here, we summarize some of the most commonly seen complexity classes. We start from the case where the growth rate stay basically stay the same, right? So your numbers of operation will stay the same regardless of your input size. So there's no growth actually. That's the flat line that we see earlier. We call it O1 or constant time algorithm. So the row over here, every row represent one category, one class, and then the growth direction is actually in the increasing order of the rows. The later rows complexity actually are growing much faster than the earlier row. So starting from constant time, you have the log time, you have linear time, you have the combination of linear time and the log time. You have a polynomial where polynomial can be arbitrary order k, right? K1 means linear, k equals 2 is quadratic, k equals 3 is qubit, so on and so forth. So K, I think the important thing over here is that it's a constant. It does not depend on the input. N is actually the input size that really depends on the input that's given to you. And exponential, we have seen this before. This is K can be any number, for example, 2 to the power of N. And finally, the most I think complex example we're going to see in this class is factorial, right? So I think, for example, the motivating example we see at the beginning of week 3 lesson, that the Olympic torch relay example is exactly in the factorial complexity class. It turns out that among all the classes that we will be introducing today, this class, factorial class, is the most demanding, the least efficient one. Okay, so suppose you want to interpret these different classes by the growth rate. This is how we will interpret them. If you have a constant time algorithm, it means that doesn't matter how you change the n. Here we double the size of n. The numbers of operation will stay the same. If you have log n, right? So here, again, of course, the exact number depends on the uh, the base of your log function, right? So if the base of your log function is 2, when n doubles, the numbers of operation will be increased by 1. And if you have linear time, n doubles, numbers of operation will also doubles. You have square, n doubles, then the numbers of operation will be increased by 4 times, quadruple. If you have exponential, I say now you cannot double anymore because it's simply too much. So you can see that instead of n doubling, n increased by 1, but n increased by 1, then the numbers of operation will already be doubling, right? Because this is 2 to the power of n. So 2 to the power of n plus 1, you have an additional multiplier too, right? So n increased by 1, numbers of operation will double. Finally, if your complexity class is factorial, you increase n by 1, it means that the numbers of operation will be increased by n times, right? So that's why factorial is the worst possible complexity that we see on this page. Okay, so the issue that we have, for example, in the previous in-class exercise, is that usually when we try to count the numbers of operations, you have a lot of terms. So when you try to convert these numbers of operation into complexity class, it's not very clean, right? So one of the very important rules when you write the big O notation is that you want to identify the terms that's dominating, and you use that dominating term to represent the final complexity class. And this is one example. Your numbers of operations, in this case, contain both exponential class and also the polynomial class. So if you write it down, what you have over here is that you have one term that's growing very fast. We know that n increased by 1, you are doubling the operation. On the other hand, right, so you have another function which is n squared, is growing much, much slower, right? So in this case, because 2 to the power of n is dominating, we say that the complexity will only be big O 2 to the power of n, exponential. Here, this is another example of domination. You have one term, this is n squared, this is a polynomial term. And then you have another term log n. We know that this is a term that will grow very, very slowly. So because of that, we say that n squared term is actually more dominating, more important. So when we write the final complexity in the form of big O notation, we can drop log n from consideration. In the previous case, we drop n squared from consideration. We can also include multiple terms that belong to the same class. For example, n squared and n cubed, n squared, and also n, right? So all of them are actually in the class of polynomial. But if you look at the order, you have this n cubed. Definitely this term will be growing the fastest, right? So when n grow to be large enough, eventually it will shadow n squared, it will shadow n. I mean, these two terms eventually become not important at all. So the highest order term is n cubed. So when we write the complexity, we will only need to use the n squared term, n cubed term, right? So I think another principle when we write down the big O notation is to ignore or drop the constant term. For example, when we write the 3n squared in the format of big O notation, this 3 over here, which is a constant, is not important. We want to simplify the writing of big O notation as much as we can. So we will simplify it to be only big O n squared. And this applies to all the other settings as well. As long as you actually have a constant coefficient, you can drop it safely, right? So we drop the constant term, we drop the term that is growing much, much slower, all right? So why do we do that? How can we be sure that this is okay? So we can use the following numerical exercise to demonstrate why we will be dropping the less important term. So this is actually a good example as well, because later, if there's any term that's not immediately clear to you, which one is more dominating, I mean, you can follow very similar approach on this page to determine who is actually more important. So this is actually a value copy from the Excel spreadsheet, right? So you can see that n value is being set. You can go from 1 to 1,000, right? Or even more. So here, I mean, you use the second column to calculate the value of 2 to the power of n. The third column is actually n squared. And then the fourth column is the actual complexity, actual numbers of operation. Now you just assume that it's 2 to the power of n plus n squared. And what you can do over here is that in order to justify that in the final writing of the big O notation, we only keep 2 to the power of n. We can calculate the fraction of the total value that is contributed by 2 to the power of n column over here, right? So as a start, when n equals 1, this contribution is 67%. But as n's value increases, you can see that just the moment you reach 20, this percentage is 100%. You cannot say that n squared doesn't contribute, it still contribute, but it's just a very, very little fraction, right? So you cannot even see it in the decimal places. So this is the reason why you can see that after you have go above n equals 20, this term n squared here doesn't matter anymore, right? So remember, when we define efficiency, we are interested in efficiency that's in the limit, with n's value to be very large. And here, this particular table proves to us that for the lower order item, and when n's value grow to be very large, that lower order item will not matter at all. All right, so the table on the right-hand side demonstrates very similar comparison. Is n squared versus log n. Right? Also over here, you can see although n squared itself doesn't grow very fast, but log n is growing even slower. You see that you go from n equals 10 all the way until n equals 100. I mean, the fact that log 100 equals 2 tell you that this log probably have the base of 10, right? Okay, so you can see that it goes very, very slowly. So the moment you reach 10, actually, the percentage of n squared is really 99%. So again, in the limit, no doubt, n squared will dominate 100%, right? Although you still have some value, this value really is nothing. That's why, in the end, we will just cross it out, right? We only need the dominating term. So if any part of this, in the previous comparison of the domination of different term is not clear to you, using Excel spreadsheet is probably the most straightforward way for you to test which term is more dominating. Okay, so now we have been exposed to the fundamentals of big O notation. We can summarize with over here with the steps that can help us derive the big O notation. Number one, I think you have to decide, particularly if it's not so obvious. I mean, sometimes some turns are being executed, some lines are being executed, sometimes it is not. Particularly if you have introduced, let's say, the if statement, right? So then you have to creatively come up with your estimation of the worst case scenario. You want to cover, in the worst case, how many operations will be induced. After you find the ways where you can induce the worst case, then you do the count. right? So this is where what we have learned in week 1 and 2 will come in nicely, right? So now you can actually count the numbers of operations by using a couple of these 4 different principles that we have introduced. Finally, after you have the count, that's usually in the function of the n value, your input size, we will convert that into the big O notation. And the key step is that we drop the less dominant term, just like in the previous 2 pages, and also we will drop the constant, right? The constant coefficients. So then we will have something that's really simple, for example, big O n squared, something like that. All the lesser terms, all the constant coefficient should disappear in your final answer, your final writing. All right, so why do we use this? What's the benefit of having big O notation? So once we have the big O notation, I think the most important thing that we can do is that now we can objectively compare the difficulty level of different problem. Right? So if you have a problem, you can imagine what is the most straightforward way you can solve it. Usually the most straightforward way will be pure enumeration. You look at like all the possible solution. You put it down, right? If you want to solve exactly, you want to do the pure enumeration of all the possible solution, how many solutions are there, right? So you can come up with certain count, then you can use big O notation to represent in the most like primitive format what will be the complexity of that problem. Then the difficulty level of different problem can now be compared, right? So I think this is the first benefit. And the second way where we can use complexity analysis is that if you have multiple algorithms, just like in the previous case, we have like 2 or even like 3 or more algorithms for GCD problem, we can compare them objectively by analyzing their complexity, by looking at their big O notation. Finally, we can use the derived complexity measure, what is the category of the big O notation to determine whether or not the problem can be solved. Uh, there's many different possible combination of the complexity term, but I think the general wisdom over here is that if your algorithm's complexity still give you a polynomial big O notation, it means that the algorithm is quite efficient. Sometimes even when the case for the case where the problem is exponential, I mean you cannot efficiently solve it, and usually it's not even scalable to realistic size. But in the later week, we will demonstrate that even the problem itself by design is exponential. We sometimes might be able to solve it by using some very cleverly designed heuristic. So this is possible, right? So we introduce that later. So what we really want, right? So particularly when we enter the real world setting, what we really want over here is that we want low degree complexity. Polynomial is okay. You can have a combination of polynomial and log. That's okay. But if you have something like this, k to the power of n, then this is probably not good. You don't want that. And factorial, definitely this is not going to work, right? We already showed that that's the worst possible complexity we can have in today's lesson. If you want to visually see like why these last 2 classes are really not very feasible, not very scalable, just look at this plot over here. On the y, right? If you look at the y, this is log scale. So which means that every tick over here, every increase in the tick over here means that you are increasing the numbers of operation by 10 times. Okay, so you see that that's why when you reach here, the way to read this is equaling 10 to a power of 19, right? A huge number. And you can see that when you are at constant all the way until polynomial, which is the green line over here, the growth rate eventually settles, right? It's still growing, but I mean, you can kind of see very clearly is slowing down to almost a flat line. This is almost a flat line. This is roughly speaking the upper bound on the numbers of operation. But if you look at the exponential, which is over here, the factorial complexity, they just keep growing. right? So it's almost like with the increase of the input size by 1, your numbers of operation increases by almost 10 times, right? So no way you can actually solve this kind of problem. That's the reason why we say that this is the only category that we'll still consider efficient. Okay, so this is another way to represent the same information, right? So if you have a very quick operation, a very quick computer, such that every operation only take 1 nanosecond, 10 to the power of 9. Or another way to say is that every second, 1 second, you can actually execute 1 billion operation, right? You can execute 10 to the power of 9 operations. Even you have this kind of computer, which is super fast, you can see that when you reach n squared, I mean, it's already quite slow, more than 100 days of solution time. And you can see that once you reach 2n, the largest problem that you can probably still solve is actually 50. N factorial is even less, right? I mean, when you reach 20, it's already 77 years. Definitely not practical. You can only solve a problem with an input size of 10 if your complexity is factorial. Okay, so this is the reason why earlier we say that faster software is actually more important than faster hardware, right? If you design your software algorithm in a more intelligent manner, right? So in this case, the example is you have a polynomial, which we mentioned is n to a power of k, right? If you have this kind of algorithm versus, for example, you have exponential, this is like 2 to a power of n, or even worse, n factorial. We want to find out what is the largest instance that you can still solve. We have this one very slow machine. This is mu, right? And this is nano, right? So roughly speaking, your faster machine is 1,000 times more faster than the slower machine, which basically is a very, very big difference. This is probably the best machine that the money can buy. But this can be our, let's say, very usual machine, very old machine, right? But you can see that if your algorithm is actually very small, just compare this part versus this part, right? Even on a very slow machine, right? But if you are able to come up with a faster algorithm, n squared, n cube, the size of the problem that you can solve is still much, much greater than the case where you just run a very slow algorithm, very ill-designed algorithm, but on a very, very fast machine, 1,000 times faster, right? But you can see that the cleverly designed algorithms still uh, defeat this faster machine anytime. Okay. So in summary, I think what really we care about over here uh, in both part 1 and part 2 is the formal definition of algorithm. This is a contract that will help you turn from a definite input to a definite output. And we say that for the given same problem from input to output, there's always more than one way to achieve that. So in order to actually choose the right algorithm, that's where the complexity analysis will come in handy. And we say that we care about the long-term growth rate. When n become very, very large, what is the estimated performance? That is the true complexity analysis that we are interested in. And we have a formal definition, formal notation that allow us to, in a very clean and very clear manner, help us to represent which particular class of the problem this algorithm falls into, right? And then we have a very clearly ranked complexity classes from the most efficient one, which is constant time, going all the way until you reach exponential or factorial. That basically tell us that you cannot really solve it in real life size problem. And basically that's it, right? So I think very simple introduction. So we need a lot of practices to allow us to master this particular process of going from the problem definition to the count and then to the big O notation, which represent the true complexity we'll be looking at. So please pause over here, spend some time to first do this conversion from the count on the left-hand side to the big O notation on the right hand side. Remember, you are dropping the dominated term, you are dropping the constant. And then we revisit the two algorithms that we have analyzed previously. We come up with the count already, count of operation already, right? So now turn those counts into the big O notation. And we have the third one, right? Which is the problem that you might be seeing in the counting based problem that we have from the previous week. Now we have learned about complexity representation. Try to use big O notation to represent the complexity of this problem over here. So while you're doing this, I think the final slides just tell you where we are. We have finished complexity. Next week, we will begin introducing the very first principle that will allow us to design algorithms, the concept of iteration and the concept of decomposition. The final page over here, I think, summarizes some of the very useful formula you may find useful for your tutorial. How to deal with the log functions of the common operation for log functions, just in case you forget about that, and the arithmetic series, right? So in today's lesson, particularly if you want to solve the in-class exercises, you will need to use a lot of these formulas on the sum of arithmetic series, right? So I think this explains how you can actually achieve that. We'll stop here, and please, again, as mentioned, spend time, work out the second part of the in-class exercises. Solution to that will be in another video.